In this video we will cover the idea behind tree of knowledge, explain how it works, and give some concluding remarks. There are many fields in which simulations are the main tool, such as meteorology, physics, systems engineering, etc. All these fields critically rely on simulations as their main tool. In social sciences, simulations are however very uncommon, even though social sciences also try to understand complex systems, just like the other fields. I believe the reason for this difference in popularity is because we know the exact behavior of fluids, particles, machines, and electrons, but we do not know the exact behavior of humans, and we thus can't make very accurate simulations of them. Currently, the following methods are used for making social science simulations more accurate: prior statistical analysis and eyeballing the simulation results. When doing prior statistical analysis, we look for a data set from which we can extract some important statistic, which we then use as a parameter in the simulation. This approach is fantastic. Unfortunately, it is however only possible for very few parameters, as it requires datasets from which the parameters can be directly extracted, and these very specific datasets mostly don't exist. The required datasets mostly don't exist because humans are these closed systems that don't allow us to look at the inner mechanism. Most parameters governing human behavior can therefore only be indirectly observed. The second approach of eyeballing the simulation results doesn't require any datasets. You simply look at how the simulation unfolded and check if this looks realistic. You can try to use this for evaluating behavior rules. This method is however not at all accurate. In this video I will present a new approach, which not only allows you to learn parameters from many different datasets at the same time, but also allows you to evaluate behavior rules on these many datasets. This new approach gives us the unique ability to indirectly learn about the inner mechanisms of humans by studying the consequences of these inner mechanisms. We can therefore learn from practically any data that was somehow impacted by human behavior. It allows us to learn all parameters very accurately, as we're learning from many different datasets at the same time. This new approach is implemented in the online platform Tree of Knowledge. Just to give you an impression of the website, its previous name was Wikipedia for Modeling Human Behavior. So, how does it work? Well, at the core of Tree of Knowledge is a human agent. Its behavior is defined by simple rules such as every year increase the person's age by 1, or at every time step we calculate the person's BMI to be their weight divided by their height squared. These here are fixed rules. We know that they're always true. But, as we're dealing with mostly unknown human behavior, there will also be many rules which we are not so certain about. In this case, we can put parameters at the place of the unknown values. For example, the following rule says that if the person's sleepiness crosses a yet unknown threshold θ1, then their goal is set to go to sleep. We will see later how, with Tree of Knowledge, we can learn these unknown parameters from data. Generally, we try to create rules in such a way that, whatever scenario we put the agent in, it will behave correctly, i.e. as a real human would. The online platform Tree of Knowledge has the following capabilities. Users can create agents and add behavior rules to them. They can upload data to Tree of Knowledge's knowledge base and, by making a digital twin of the real-world system that produced the data, we can learn the unknown behavior rule parameters from the data. Finally, we can use the fully learned agents to make predictions. So, in the following sections I will describe in further detail how the data is brought to the model, how parameters are learned, how the uncertainty in the parameters is quantified, and how we can evaluate agents' behavior rules. For sake of brevity, the making of predictions will be subject of a future video. Also, I will illustrate the next sections using the following example, determining the birth probability of a woman. That is, for every year in a woman's life, what is the probability for her to have a child in that year? This might depend on factors such as how many children she already has, her marital status, and her age. So, Let's create the following rule for calculating the birth probability. It is a logistic regression depending on factors such as age squared, she has 1 child, 2 children or more, and her marital status. We however don't exactly know how it depends on these factors, so we have all these unknown parameters. The main reason for us using a logistic regression here is because it outputs a value between 0 and 1, and we want the birth probability, being a probability, to also be a value between 0 and 1. Here's a screenshot from the actual tool, showing the rule we created. We can see that it's the exact same here, just that the parameters now have names, such as weight age squared, etc. The next step for us is to learn these unknown parameters from data. We will learn the parameters of the birth probability rule using 2 very different data sets, the National Longitudinal Survey of Youth and the fertility rates by age of mother. The reason for us using these 2 very different data sets is to show some of the wide range of data sets that can be used in tree of knowledge. It is worth noting that using common statistical techniques and models, it is not possible to obtain the birth probability parameters from either of these 2 data sets, as the data sets only measured indirect consequences of the birth probability. Let's first look at the National Longitudinal Survey of Youth. This survey had 30,000 participants. In 1979, the participants filled out the first survey, then some years later they filled out the same survey again, and then again at irregular intervals. All surveys contained the same questions, such as, how many children do you have? What is your marital status? What is your employment status? Etc. This is what the data from the surveys looks like. We can see that the participants left many fields blank. The first step in our analysis is to upload the dataset to Tree of Knowledge's knowledge base. For any data point that has been uploaded to the knowledge base, we now know from what object it comes. In this case, it's the person with identification 1. The attribute is age. This data point is valid from 1979 to 1980. The source of the data was the US Bureau for Labor Statistics, and we know some other facts. This knowledge allows us to draw individual data points from the knowledge base and combine them to a timeline. We let Tree of Knowledge automatically create these timelines for the women that participated in the National Longitudinal Survey. We know their state in 1979 from the first survey, and from the other surveys we know their states in later years. Now, we separate this data into data for the initialization and for the validation. That means we initialize the simulation with the state from 1979 and then run the simulation, i.e. at every time step we apply the behavior rules to calculate the values for the next time step. Now we can use the validation data to check how accurate the simulation was. Ideally, we would want the simulation to exactly reproduce the participants' lives. We can therefore measure how accurate the simulation was by comparing the simulated values with the true observed values. In our case, we are mainly interested in correctly simulating the number of children, as it is the only variable that is influenced by the birth probability. By comparing the simulated values with the true values, we calculate a score. The higher the score, the more accurate we know the simulation to be. Learning parameter values. Now, this simulation for which we obtained a score was run using some random values for the birth probability parameters. Those were the parameters from the birth probability rule. So, if we run the same simulation with other parameter values, then the birth probabilities will be different and the simulation as a whole will unfold differently. We will therefore also get a different accuracy score. We can now try out many different parameter values and see for which values we get the highest score, i.e. the most accurate simulation. We can then call the parameters that give us the most accurate simulation the best parameter values. Just to show you that this is indeed what the tool does, here are 2 screenshots from it. This blue line is the simulated number of children for this woman. We can see that she's simulated to have 2 children early on and then some years later a 3rd child. The green values are the true values, which we know from her survey in 1999 and 2005. So This simulation is not very correct because she simulated to have altogether 3 children. In her surveys she however said that she only has 1 child. For the woman below, however, the simulation was correct because it correctly predicted her to have no children. Now, I'd like to show you how we can learn the same parameters using a very different data set. The fertility rates by age of mother. This is what the data looks like. We can see here the fertility rate for American women aged 20 to 24, the fertility rate for women aged 25 to 29, etc. So we have here the fertility rates for different age groups of American women. This data came from the American state observing all American women. We could describe the system to have the following agents: the country America, and then many women who all have the American nationality. So, to analyze the fertility rate dataset, we do the same things we did before. We first upload the data to the knowledge base, then we create the agents that make up the underlying system, and automatically populate these agents' timelines with data from the knowledge base. Now, the knowledge base is an integrated repository of all the uploaded datasets. So in practice that means the fertility rates come from the dataset we just now uploaded. The data on American women comes from the National Longitudinal Survey that we had uploaded earlier. And there might be other data about America coming from other tables which we or other users had uploaded previously. Now, we don't actually need all of this data, we only need this, which is the data used for initialization and validation. So, here we do the same as before. We initialize the simulation with the initialization data, and then we run the simulation to get all the other time steps. It is important to note that in the simulation the fertility rates were calculated by averaging the birth probabilities from the simulated women in the correct age group. By comparing the simulated fertility rates with the true fertility rates, we can now determine how accurate the simulation was. This simulation here was run using some values for the birth probability parameters. The parameter values of the birth probability rule affect the birth probabilities of the simulated agents, which in return affect the simulated fertility rates. So by trying out different parameter values, we can again see which values give us the most accurate simulations. These are the best parameter values, which we learned by fitting this simulation model to the fertility rates dataset. So to recap what we just now did, we first learned the birth probability parameters using the National Longitudinal Survey, and then we learned them with the fertility rates dataset. These two datasets are very different. The first dataset contains information on individual people, and the second dataset contains information about the country America. But we were still able to learn the same birth probability parameters from both of these datasets. In fact, Tree of Knowledge allows us to learn the birth probability parameters from pretty much any dataset that was somehow affected by births. This could be time series data or cross-sectional data. Cross-sectional data is data coming from a single time step. So what we do here is run the simulation also just for a single time step. We can, for example, calculate a y value and then compare this to the correct value. In our example, the rule used for calculating the birth probability is a logistic regression. We can, however, use any calculation or set of calculations as a rule. This includes most machine learning and statistics models, rules to create or destroy network connections, etc. I know of no behavior which we couldn't model with behavior rules. Quantification of uncertainty. So here's what we did again. Using the two datasets, the National Longitudinal Survey and the fertility rates, we learned the birth probability parameters. We can display the learned parameter value like this. Here the value 2 is a line a bit further right from 0, and the value 2.2 is a bit further right still. But in fact, Tree of Knowledge does not learn single optimal parameter values like this, instead it learns probability distributions. These are Bayesian posterior distributions that contain all the learnings obtained from the datasets. Let's compare optimization and Bayesian inference. The advantage of optimization is that it's more computationally efficient. Bayesian inference, on the other hand, prevents overfitting, which is fantastic. It also gives us an exact quantification of uncertainty. So the width of the distribution gives us the exact uncertainty for the learned parameter. If we, for example, use a bigger dataset, then the distribution will be narrower, i.e. we will know the parameter more exactly. And the posterior distributions we obtain from the Bayesian inference are part of the rigorous framework which is Bayesian statistics. We can therefore use standard Bayesian statistics to combine the two distributions we inferred from the two datasets to a new distribution. This combined dataset contains all of the learnings from the National Longitudinal Survey and the fertility rates. We can, for example, see that the new distribution is narrower. That is because it was effectively learned from more data. Here's a screenshot from the tool that shows how we're combining the posterior distributions from the National Longitudinal Survey and from the fertility rates. So what is the advantage of learning posterior distributions from different datasets and then combining these posteriors to one joint distribution? Well, for one, the more data we use, the more accurate the combined posterior will be. This is much like meta-analysis, just that we don't require datasets to come from very similar experiments. We can use very different datasets with observations from very different systems. This factor is very important for getting as accurate as possible behavior rules. The second factor, however, is even more important. The real world is messy, and for the most datasets there are some small effects at play which haven't been accounted for. There are many possibilities for small errors, even with the best designed experiments. This leads to slightly wrong parameter estimations. As the datasets here are, however, observations from very different systems, each dataset has different errors. By combining the estimates from these different datasets, the errors average out and we get closer to the true generalizable effect. Evaluating behavior rules. The birth probability rule we created earlier was just a guess. We thought that the birth probability might depend on factors such as age, the existing number of children, the marital status, and that we could maybe use a logistic regression. But these were all speculations. We could, for example, have used this set of rules instead. The first rule sets the birth probability to 0. The second rule adds on the influence of age. Then the next adds on the influence of having one child, 2 children or more. And then we add on the influence of being married or not. This set of rules is an equally valid hypothesis for the birth probability. Just by looking at them, we couldn't say which of these two options is better. With tree of knowledge, we can however test which is better. So, what we do is run the existing simulations with this behavior rule and see how accurate the simulations are, i.e. how well the simulations match reality. From both models combined, we here got an accuracy score of 61. Next, we run the same simulations, this time however with the new birth probability rule instead of the old one. And we can then see how accurate the simulations are with this new rule. In this case, the first rule got a higher overall model score, which means it created more accurate simulations. We can therefore call it the winner. There's little point in using the other rule as it doesn't perform as well. This was actually a little simplified. In reality, we use a thing called Bayes factor for comparing behavior rules. It works in a very similar way, but is more statistically rigorous. So, to conclude, Tree of Knowledge has at its core a behavioral model of humans. A researcher with their dataset can now add new behavior rules to the behavioral model to make it work correctly in the scenario they're investigating, fit these behavior rules to their dataset or other people's datasets, and evaluate and improve the existing behavior rules on many datasets. By doing so with more datasets, the model of humans becomes increasingly accurate. It also gets more accurate when other researchers investigate their own questions by using it to model their very different datasets. The result is a model of human behavior that is widely applicable, i.e. it behaves correctly in many scenarios. It is accurate because it has been learned and evaluated on many datasets, and it is rigorously tested. This last point, concerning rigorous testing, is a very important point. I always thought it remarkable how good our understanding in the physical world is, and how strong our confidence in rules such as F equals ma are. We often call them natural laws. It is however important to realize that F equals ma was just a hypothesis, a guess from Newton. The thing that gives us this great confidence in its correctness, and lets us call it a natural law, is that we were able to observe this rule in scenario after scenario. Now, tree of knowledge lets us do something very similar. It allows us to hypothesize behavior rules and then test them in scenario after scenario. So, to summarize, tree of knowledge allows us to create a model of human behavior. Because of its innovations, we can learn parameters from multiple datasets and evaluate behavior rules with multiple datasets. This allows us to get an increasingly generalizable and accurate understanding of human behavior.